Professor Dave here. Let's talk about sequences.
He knows a lot about all kinds of stuff. Professor Dave explains.
Let's count some numbers, shall we? 1, 2, 3, 4. What are we doing exactly? We are generating a sequence of numbers, which happens to be the natural numbers. If a particular term in the series can be represented by a sub n, and the entire sequence is a sub n in brackets, then this sequence could be represented by the letter n, instead of writing out all the numbers. This means that a1, the first term of the sequence, when n equals 1, is 1. To get a2, the second term, n must equal 2, and we get 2. Now let's list all the even numbers. 2, 4, 6, 8. How would we represent this series? That would be 2n. A1, where n equals 1, gives us 2. A2, where n equals 2, gives us 4, and so forth. What if we do the natural numbers again, but start with 2? Now the first term is 2. The second term is 3, so we can represent this as n plus 1, where every term is 1 greater than its chronological number in the sequence. We can generate sequences using any expression like this, and they can get pretty complex. Try 2n plus 3. The first term would be 5. The second term would be 7, and then 9, 11, 13. Sequences like this are called arithmetic sequences because each term differs from the previous by a constant amount, in this case by 2. But not all sequences work this way. There are also geometric sequences, where each term can be attained not by adding a constant to the previous term, but by multiplying the previous term by a constant. Something like 2, 6, 18, 54. Each term is 3 times the previous. Can you figure out how to represent this sequence? It starts with 2, and then you multiply by 3 once more for each term. So this should be 2 times 3 to the n minus 1. Some sequences fall into neither of these categories. What about 2 to the n minus 1? We'd get 1, 3, 7, 15, 31. In every case, we just plug the numbers in and see what we get. If a sequence has a domain that includes all positive integers, meaning that starting from 1, you can keep plugging in numbers all the way to infinity, this is called an infinite sequence. All the ones we just looked at are examples of infinite sequences. If instead the domain stops at some integer, it will be a finite sequence. There are also sequences that are derived not from an expression like this, but exclusively from the previous terms in the sequence. A famous one of these is called the Fibonacci sequence. This one starts with a 1, and then another 1, and then every term after that is the sum of the previous 2. 1 and 1 is 2. 1 and 2 is 3. 2 and 3 is 5. 3 and 5 is 8. We continue in this manner to get 13, 21, 34, and so on towards infinity. This sequence uses a recursion formula, meaning that we can define any term a sub n by previous terms. In this case, a sub n will equal a sub n minus 1 plus a sub n minus 2. With these expressions referring to the term immediately prior the term in question and the one 2 before. Another type of sequence that does this can be found with factorial notation. The sequence n factorial, with factorial being represented by an exclamation mark, is equal to n times n minus 1 times n minus 2, all the way until we get to 1. For example, let's list the values of n factorial for the first few natural numbers. We can see that in each case, we start with the number we are evaluating and multiply it by every single smaller positive integer in descending order. Factorials are similar to exponents in that they only operate on the number they directly follow. This is an important concept to understand, as we will frequently see factorials in sequences. Say we have 3 over n plus 1 factorial. Let's plug in 1 through 4 to get the first 4 terms in this sequence. And doing the arithmetic, these are the values we should get. Now that we understand sequences, we can move on to sums. Summation notation takes a sequence and then instructs you to find the sum of a certain number of terms in that sequence. For example, let's just start with this first sequence we looked at, with the natural numbers. But instead of a sub n, let's write a sub I, since this is a slightly different application, although technically we could use any letter here. If we place this uppercase sigma here, we can put I equals 1 just below it, and then any integer above it, like 5. What this says is that we have to add up the first 5 terms in this sequence. That would be 1 plus 2 plus 3 plus 4 plus 5, which is 15. In this case, 1 is the lower limit of summation, and 5 is the upper limit of summation. Let's try some examples. How about the sum of k squared plus 2 to the k from 1 to 4? To get this, we have to evaluate the expression for each number in the domain first, and then we add them all up. For 1, we get 3. For 2, we get 8. For 3, we get 17. And for 4, we get 32. Let's add those up, and we get 60. Easy enough, right? Now, what if we go in reverse? What if we have a sum and we have to figure out how to express it in summation notation? This is a little trickier because we have to recognize the pattern in the numbers. But let's give it a shot. How about this one here? 1 plus 4 plus 9 plus 16 plus 25 and continuing. What is this? Well, it's the list of perfect squares. We could rewrite this as 1 squared, 2 squared, and so on. That means we could write this as the sum of n squared from 1 to infinity. We could also truncate it at any particular term, like after the 5th one, and then make the upper limit 5. How about this one? 1/2, 2/3, 3/4, 4/5, and so on. Well, the top number in the fraction is equal to n, but the denominator is always 1 more than that, or n plus 1. So it's n over n plus 1. Things can certainly get trickier. How about 3 over 4, 6 over 5, 9 over 6, 12 over 7? Here, the top is clearly multiples of 3, so that's 3n. On the bottom, it goes one at a time, but starting with 4, so that could be n plus 3, where it's always 3 more than the number of the term. As long as we always think logically in this manner, we can usually figure out even the toughest sequences. We just look for the patterns that are present. To wrap things up, let's take our new understanding of sequences and factorials and show a novel derivation for the natural base, e. Isaac Newton showed that e will be equal to 1 plus 1 plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, and so on to infinity. If we work out the first few terms, we get 1 plus 1 plus 1/2 plus 1/6 plus 1/24, and by now we already have e to a few decimals. This sequence is interesting because while it is an infinite series, it has a finite sum, the number e. This is different from other infinite series, like the sequence of natural numbers, which is an infinite series and an infinite sum, because we can never add up all these infinite numbers. This brings up the notion of limits. In the limit of n equals infinity, this series has a finite sum. Sums and limits will be a big deal in calculus. So as we can see, sequences, though they sometimes seem abstract and arbitrary, actually crop up in nature, not just as representations of mathematical constants, but also in the form of intricate biological designs, examples of the ways in which mathematics can produce stunningly beautiful physical forms. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.